All right, let's make some bigger diagrams. So we did hydrogen, so we did H2, we did helium, He2. Let's go down to the second period and do the homonuclear diatomics. So for dilithium, Li2, I'm going to make my MO correlation diagram. So I have my energy label. My column on the left will be my lithium atomic orbitals. On the right will also be lithium atomic orbitals and lithium 2 molecular orbitals in the middle. Lithium is in the second period, so it has the 2s and 2p. We'll get to 2p in a minute. We're just going to deal with 1s and 2s because both of those have electrons in them. My 1s atomic orbital will overlap with the other 1s atomic orbital. So in these, you need the same orbital, but you also need the energy needs to be close enough to overlap. So it will be 1s and 1s. I'll get a sigma 1s at a lower energy and a sigma star 1s at a higher energy. I've got my dashed lines to connect my AOs to the MOs that they combined to make. And that's everything that 1s would make. Then my 2s orbitals, they would overlap in the same way. It's just now that it's a 2s, so it's further from the nucleus, higher in energy. I will still get a sigma, that's sigma 2s, and a sigma star 2s. For the electrons, each lithium brings in 3 electrons, so I have those here in gray. And the atomic orbitals, that means I have 6 electrons total to fill in for my molecule, starting at the lowest energy. So 2 in the sigma 1s, 2 in the sigma star 1s, 2 in the sigma 2s. When I go to calculate my bond order, I will count everything that I see. So from the 2s and from the 1s. So the bonding MOs are highlighted in orange. I have 4 electrons in my bonding MOs. Antibonding is in pink, 2 electrons in the antibonding MO. So half of 4 minus 2 is 1. So, I mean, it looks like dilithium, you would probably say it exists, has a bond order of 1. The thing that is coming in the second period, so I have this bracketed in green. We're in the second period. The 1s are considered core electrons, core orbitals by this point, and they will always be full. So in every calculation that we do, it'll cancel out for a bond order. So it is okay to leave off the 1s from your MO correlation diagram and from your bond order calculation. So if we use the valence electrons only, for example, for dilithium, to calculate the bond order, now I'm ignoring everything in 1s. I have 2 electrons in my sigma 2s and 0 electrons in my sigma star 2s. My bond order would be half of 2 minus 0, which is 1. So I'll get the same answer by just dealing with the valence electrons. And if I drew pictures, well, 2s orbitals overlapping in a constructive and destructive way, well, it looks exactly the same as 1s. So that's what these pictures would look like, exactly like the same pictures we had for 1s, although technically bigger. We just don't have a scale on our paper. Okay, so what about p orbitals? Second period, each element has a px, a py, and a pz. The px orbitals, right, these are atoms side by side, we're bringing them close together. The px orbitals, when they interact, it is a sigma interaction. So those orbitals are pointing at each other. That's the kind of overlap that you get. So the constructive interference version, or they are both shaded in or unshaded appropriately so that they're the same shade when they overlap. The result is a sigma 2p bonding MO. And this picture, right, it looks like how I wrap presents because I'm bad at wrapping presents, right? The candy method where it's big in the middle and kind of smaller on the sides. But based on the interaction we've done, the on the sides part, that's a normal p orbital lobe size, and the middle is like two p orbital lobes combined together. On the right, I have the anti-bonding interaction. So if these p orbitals, px orbitals, were brought toward each other with destructive interference, we would end up with a node in the middle. And the lobes that are pointed toward the node would probably be like shrunk a little bit, um, which I don't have shown very clearly in this picture, but that's okay. What matters is you have the node, you have the shading correct, which is that shaded and unshaded interact. It doesn't matter which side is which. This is a sigma star 2p anti-bonding molecular orbital. For py and px, the results are the same because they are orbitals at the same energy doing the same type of overlap, but I am going to draw all the pictures separately. So for py, I could bring them together constructive interference or destructive interference. And for the constructive, these are side by side. So it is a pi interaction, is a pi 2p bonding. And so my picture, it looks like my top two lobes smashed together and my bottom two lobes smashed together. The destructive interference version, it's still side by side, so it's still pi. It is a pi star 2p anti-bonding molecular orbital. So destructive interference, I get a node and nothing overlaps or combines. Okay, PZ, well, PZ plus PZ, it's the same as the PYs, but rotated 90 degrees. So my PZ orbitals coming out, going back, side by side with another PZ, constructive interference would give me a pi interaction made with 2p orbitals, and it is a bonding interaction. So I get another pi 2p bonding. And if I draw the combined picture, right, I have a constructive lobe pointing out, a constructive lobe pointing back. It looks like the pi 2p bonding that I drew for py, but rotated 90 degrees. The anti-bonding combination, so my destructive interference, it's a pi star 2p anti-bonding. I get a node, my shading is staggered, but they're pointing out of and behind the paper board, etc. So 4 combinations from 4 orbitals, but right, the pi 2p bonding, they look exactly the same but rotated. They will have the same energy. So just a reminder that degenerate is the word that means same energy. So the pi 2p bonding have the same energies, and the pi star 2p antibondings have the same energy. What does this mean? Okay, what this means is we can put together diagrams to make MO correlation diagrams for the homonuclear diatomics across the second row. We're not going to go below the second row for MO theory, so that's a good thing, I guess. The ordering, which was determined experimentally, you'll see it slightly different for some parts of the periodic table than it is for others. I am going to give you these diagrams, and yes, I do want you to know the diagrams. So side by side, I'm going to give you the MO correlation diagram, that the outline with all the components you need except for putting in the electrons for B2, C2, and N2. And then I'm also going to give it to you for O2, F2, and Ne2, because that's the split. So boron, carbon, nitrogen have one ordering of their molecular orbitals. Oxygen, fluorine, and neon have a different ordering for their molecular orbitals in the correlation diagram. All right. So for boron, carbon, and nitrogen, if I put all of this together, right, I have an energy scale. I have my atomic orbitals on the outside, my molecular orbitals in the middle. The atomic orbitals that I'm dealing with are 2s and 2p, and they are going to combine with each other to form the molecular orbitals that we have just described and put pictures to. Now I'm leaving off the core, so I don't have 1s on here. You could include it if you want to. For the 2s, right, the 2s overlaps with the other 2s. I get a sigma 2s and a sigma star 2s in my molecular orbital for the diatomic. When the p orbitals overlap, in boron, carbon, and nitrogen, the lowest energy is the pi 2p, and I have two orbitals that are pi 2p interactions. So I'm going to put two lines because I have two orbitals that are the same energy. I can put 4 electrons at this level because I have two orbitals to hold them. Then after that is the sigma 2p, just the one. And then above there's the pi star 2p. Again, there are two pi star 2p's, so I'm going to draw two lines. And then the sigma star 2p has the highest energy. That is the ordering for boron, carbon, nitrogen, MO correlation diagram. This is also sometimes called the second order correlation diagram, and we can talk about why. You don't have to know why, but if you're looking for a way to help you name it and differentiate it, it's second order. Let's go through the first order diagram and then highlight the differences and maybe do a tip or a trick for remembering this. So on the right, oxygen, fluorine, and neon. I would still have an energy scale. I would still have my outside columns of atomic orbitals, my middle column of molecular orbitals. The atomic orbitals are still 2s and 2p. I've left off the 1s. My 2s orbitals will still give me a sigma 2s and a sigma star 2s at the lowest energies. My p orbitals, now my lowest energy is sigma 2p. The next energy is pi 2p, and there were two pi 2p's, so I have two lines. And then the highest energies are in the same order they were before, pi star 2p, and then sigma star 2p. So almost everything is the same for this diagram. The only thing that has changed, which I have highlighted with an orange box, is the ordering of the bonding orbitals made from p atomic orbitals. So in boron, carbon, nitrogen, the pi 2p is lower than sigma. In oxygen, fluorine, neon, the sigma 2p is lower than the pi 2p. Now, the one on the right is called first order. So the things that I've used to remember this or to get my brain to do it in the right order, the first half of the p block uses second order, and the second half uses first order, which that's a little crisscross weirdness. However, the good news is that in second order, the level with two orbitals is the lowest. So in second order, it's the pi 2p. So second order is 2 and then 1. First order is 1 and then 2. So in first order, the sigma 2p is lower than the pi 2p. Again, these were determined by calculation. I would like you to know these and be able to put them together. And you know what? We should do an example. It's always good to have an example. Let's check this against O2 and see what it tells us because, right, O2 is given as an example for why valence bond theory doesn't always work. Let's see what it looks like in MO theory. So O2, I have my energy diagram, my oxygen atomic orbitals in the outer columns. So I have a 2s and a 2p. And if I'm just doing 2s, 2p, I have 1, 2, 3, 4, 6 electrons total. 2 in the 2s and 4 in the 2p for each. Now, oxygen is in the second half, so it will be first order. So when I'm filling in my oxygen MOs, so my MOs for O2, I have sigma 2s as the lowest, sigma star 2s after that, then second half, first order, sigma 2p comes next, then pi 2p, then pi star 2p, and sigma star 2p. So if each oxygen is bringing in 6 electrons, I have 12 electrons total to fill in my MOs. So starting from the lowest energy, everything pairs up, right? I have 2 in the sigma 2s, 2 in the sigma star 2s, 2 in the sigma 2p. When I get to pi 2p, I'm going to put 2 electrons with spin up in separate orbitals and then go back and start to pair them up. But it still ends up full. So I have 4 electrons in that level. But then I only have 2 electrons left. And I'm at the pi star 2p. Electrons don't pair up unless they have to, even in MO diagrams. So I have these 2 unpaired electrons that show up in my MO diagram that do not show up in the other models. So these are the 2 unpaired electrons that we are seeing experimentally, and that's where they are. They're in a pi star 2p molecular orbital in O2. We can do a bond order and compare it to the Lewis structure. So we've had the O2 Lewis structure up here before. For my bond order, sigma 2s, sigma 2p, pi 2p are the bonding MOs, highlighted in orange. Sigma star 2s and pi star 2p are my antibonding, highlighted in pink. Now, I still have one more antibonding. It just didn't have any electrons in it, so I didn't highlight it. 1/2 of 8 minus 4 is 2. So my MO diagram shows a double bond, which matches with my Lewis structure. So in this case, these 2 theories match, but the Lewis does not show the unpaired electrons that do exist. Okay, so practice, if you would like, do N2 and see how that compares to the Lewis structure.